Hi guys, my name is Ashley Colchado, and today I'll be talking a little bit about my Lab 3 black hole in orbit. Here are some purposes and a little result preview from my lab. The first purpose was to use GlowScript to analyze a star's motion to determine the mass of the black hole, and the mass of the black hole ended up being around approximately 1.85 kilograms. And then the second purpose of this lab was to use the mass of the black hole to find the initial velocity of a spaceship to get close to the black hole without crashing, and the ship speed ended up being, as you can see down below. And then the third purpose was to use the mass of the black hole to find the initial velocity of a spaceship to not crash into the planet. And down below, you can see the approximate ship speed. Some equations I used for the lab were Newton's second law / momentum principle, where it states that a system's change in momentum is proportional to the net force, where F net equals delta P over delta T. The velocity update formula, where final velocity is equal to initial velocity plus F net over mass times delta T. And then also, similarly, the position update formula, where final position is equal to initial position plus average velocity times delta T. And then I also use the parallel and perpendicular components, where F net equals F parallel plus F perpendicular. And then also the universal gravitational force equation. In part one of this experiment, I found the mass of the black hole, and this was my experimental setup, where the system was the star and the surroundings was the black hole and everything else in space. Some initial conditions here are the star's mass, delta, and the gravitational constant. This is my computational model, or part of it. You'll see some more in some other slides, but a lot of this is copy pasted and not meant to be altered. But as you can see, the things highlighted here in yellow were things that I changed. So some things being the mass of the star, the time interval, and then the initial and final momentum vectors, and then also how to calculate dp over dt, and then Newton's second law, dp over dt parallel, and then dp over dt perpendicular were also altered. And then here, I did have to edit these 7 lines to find fnet parallel, and then fnet perpendicular. And this was my result. In part 2, the objective was to orbit and not crash. So my experimental setup was very similar, but the system was the spaceship this time, and the surroundings were the black hole, the planet, and everything else in space. So some initial conditions that I kept were the star's mass, spaceship mass, and planet mass. Similarly, a lot of this computational model remained the same from the copy and pasted model, but the things in yellow were things that I changed. So just some net forces on the moon and then some net forces on the spaceship had to be altered in order to get the final result. And then here I had to update Newton's second law and the position update formula. And this was the ship speed and the final result. Some possible reasons for error could be external forces that weren't accounted for, or there could have been a closer initial velocity. And I think just having the time to interval run for longer may have been helpful to prevent some error. So, what does this mean? Net force is the same as the rate of change of momentum, and it's easier to find rate of change of momentum. There's less factors that have to be known to calculate it: object mass, velocity, time interval. So, what if finding the spaceship's initial velocity without crashing into the planet or black hole? Um, this is what ended up being my result for this, and also what ended up being my initial velocity for that. So, yeah. Thank you.